All right, so I'm ready to get started. Like I said a minute ago, I tried to pick problems, at least one of each type, that she said would be on your test. Of course, I can't do every variation of every type, so if you have any additional questions, make sure that you ask. And I'm going to try to see what other videos I have that are related. I do have lots of related videos, but many of them are more complex than what she typically would give on an exam, and so I'm hesitant to put those in the playlist because I don't want someone to see them and say, I didn't know we had to know like how to do one this complicated. So and most of the videos I have are more complicated, but I will see what I can find. So before I get started with these problems, are there any questions? All right, and Zoom people, y'all can hear me and see my screen.
Yes.
Okay. All right. Okay, so here we go. First one, use mesh analysis to determine the amount of power supplied by the voltage source. So this is an older problem, but oldie but goodie. You need to know how to do mesh analysis. So we'll put a little circuit, a little current in each mesh here. And I'll call this one I1, and this one I2, and this one I3. And I recommend that you do them all either clockwise or counterclockwise. Mr. Rabelais, who you'll have next year, will tell you you don't have to do that, which is true. You don't have to do that. I am not organized enough to keep track of doing some one direction and others the other direction. So when you do them all the same direction, you can be guaranteed that any shared branch is like I1 minus I2 times the resistor on that shared branch, and so I like to do it that way. So when I look at my first mesh, I see the way I've drawn I1 has it going in the same direction as this current source, and there's no other current going through that current source, so I1 has to be 9. So I can just say I1 is 9, and I don't have to do anything else with that first mesh. And then the second mesh, as I come through the shared resistor, I know that that will be 2 ohms, and then it'll be I2 minus I1. And that's what I meant by saying if you draw them all going clockwise or counterclockwise, the shared ones will be like that. Which means that on the other side, I have 4 ohms, and it'll be I2 minus I3. And that has to equal 0. And then in the last mesh, I'll start at the 4 ohm resistor. I'll be 4 is I3 minus I2. And then the top resistor is only I3, so plus 8 I3. And I think I do this differently than y'all. I put everything on the same side. I see that it's coming into the positive terminal of the 40 volt voltage source, so I do plus 40 equals 0. If it was going into the negative side, I would have said minus 40 equals 0. I think I've seen y'all put the voltage source on the other side when you write them. Maybe? Don't know? Okay. Well, then I'll just keep doing it my way. So when there's the voltage source, when it has the sign of whatever terminal it's entering the plus side, so it'll be plus 40. So theoretically, I have 3 equations and 3 unknowns. If you have that, you're probably missing something because you're probably not going to have 3 equations and 3 unknowns on the test. And we have that I1 equals 9. So we really only have 2 equations and 2 unknowns because I can replace I1 with 9. So that's my first equation. My bottom equation, I'll distribute my resistor values, and I'll take my constant to the other side. And then the top equation, I'll have 2I2 minus 18. This should have been I2 minus I3, not I2 minus 3. So 2I2 minus 18 plus 4I2 minus 4I3 equals 0. And then the second equation, minus 4i2 plus 12i3 equals negative 4. That's not, yeah, is that right? Yeah, that's right. And then the top equation, combining like terms, 6i2 minus 4i3 equals 18. On the bottom equation, just to make solving easier, I'm going to divide everything by 4. So minus I2 plus I3 equals negative 10. So now I'm just solving, just doing algebra. The top equation, I'll divide everything through by 2, just to make those numbers smaller. 3I2 minus 2I3 equals 9. And then I'll multiply the top equation through by 3. I get minus 3I2 plus 9I3 equals negative 30. And that gives me 7I3 equals negative 21, or I3 equals negative 3 amps. I'll come back, I'll show that back again in a minute. I3 equals negative 3 amps. I just wanted to see what the problem was asking. Okay, so let me get back so y'all can copy that if you want. And the question, the actual question was, find the power supplied by the voltage source. So since it says find the power supplied, then I can I should get a negative number for my answer, but I'll list it as a positive number because you say that positive power is supplied. So when I look at my circuit, I see that in this last mesh, I'm just copying the last mesh over. I3 is in fact the current going through that voltage source. If that voltage source was somewhere else in our circuit, I might have to solve for another component of it. But since it's the one going through that voltage source, since I3 is the only current going through that voltage source, I can use it to find the power. So power is IV. The current I3 is going into the positive terminal, so I'll list that as 40 volts. And the current that is going into the positive terminal is negative 3 amps. And so my power is negative 120 watts, or I would say 120 watts power supplied. Now, let's say, for example, that instead, if our voltage source was right here, if our voltage source was right there, then we'd have to be careful what current we use. And so let's say our voltage source was on that middle branch. We have I2 going this way and I3 going this way. So the current that I would want to use would be I2 minus I3, because I2 minus I3 would be the current that's going down into the positive terminal. Because both currents I mean, there's just one current in the branch, but the way it's made up of the I2 and I3 components. Do y'all see what I'm talking about there? Okay. All right. Are there any questions on this problem before I go on to the next problem? Why is the 40 positive? Oh, well, the power here is negative, but that implies supplied. And so when you say supplied, you don't put the negative.
No, it's just the magnitude.
Yes, right, right. So when you use the word supply or absorbed, you just use the magnitude. Yeah. But if you just were to write the answer, power equals negative 120 watts, I wouldn't do that if the question said find the power supplied, because it's specifically asking for supplied. I would want to be really careful, and I'd write out 120 supplied. And it's just because there was one professor who taught circuits a while ago who really was very picky about that. I doubt that it would be a big deal here, but I did want to make sure that y'all knew the difference. Okay, any other questions? And if y'all can also help me keep an eye on the chat, so in case something comes up. Let me ask y'all this. Normally when I have SI sessions, I stop after each problem and save it, and then I upload them separately so that people can watch just the problem they want, and they don't have to go through the entire video to watch it. But that would mean, since I don't have a place to post links, that it's like I can easily give everybody one link for the whole video. What's easier for y'all? Would y'all rather have the whole thing in one video? Okay, nobody cares. All right. Okay, all right. Then problem 2. All right, so here we're using nodal analysis to determine IX. So first we need to determine what our nodes are going to be. So I kind of sort of, well, not, I do have a node here, but I don't have to find it. I know that if I call this ground, that this node is 12.3 volts because it's on the it's 0 on this side because I labeled it ground, and then I have a voltage source, and your voltage is always the number on the voltage source. It's that much more on the positive side than on the negative side, so it has to be 12.3 there. And then that leaves me with 2 other nodes, so V1 and V2. And I'm not going to worry about the IX. It looks like I have to worry about the IX because of my dependent source here. So I'm going to go ahead and write down what IX is in terms of my nodes. So remember, whenever you have a current, so there's a current, and I have a voltage on this side and a voltage on this side, and I've got a resistance, then the current equals the voltage. If you look at the direction the current is going, the voltage from where it's starting minus the voltage on the other side over the resistance. And so IX here equals 12.3 minus V1 over 10, or I can write that as 1.23 minus 0.1 V1 is IX. Okay, now I'm going to write my nodal equation for V1. So going to the left, I have V1 minus 12.3 over 10, plus going down, I have V1 minus 0 over 4, and going to the right, I have V1 minus V2 over 20, and that equals 0. I'm just since I'm right here, I'll go ahead and multiply this through by 20, and I'll get 2v1 minus 24.6. Y'all please stop me if you see me make a mistake. Minus 5v1 plus v1 minus 2 equals 0. Or this is v1 minus v2. So that's minus 3v minus thank you. Yes, it should be. So that makes this 8v1 minus v2 equals 24.6. And then my equation at v2 is v2 minus v1 over 20. And then currents coming in are negative. So it's minus 2ix plus v2 minus 0 over 2. That's the current going this way. And then the current going up is v2 minus 12.3 over 5 equals 0. Now I'll multiply this one through by 20, and I get v2 minus v1 minus 40ix plus 10v2 plus 4v2 minus 49.2 equals 0, or v2, that's 11v2, 15v2, minus v1 minus 40ix equals 49.2. Now we know what ix is. Ix is 1.23 minus 0.1 v. So 15v2 minus v1 minus 40 times 1.23 minus 0.1 v1 equals 49.2, or 15v2 minus v1 minus 49.2 plus 4v1, really, equals 49.2, which all simplifies to 3v1 plus 15v2 equals 98.4. And I've already probably made a mistake, but at this point I'm not willing to try to do this one without some help, so I'm going to get out the calculator. Anybody see a mistake I made? Okay. So you will definitely hear me say this if you come to any of my SIs next semester, but I really, really like this calculator. It's the TI 36X Pro. It's just awesome. And for instance, I can tell it I have a 2x2 system, and my coefficients are Can someone tell me what my coefficients are? Was it plus or minus?
You did E1 first, or was 8 first? 8, and then -2. Or
8,
8
8 minus 1?
and equals positive 24.6.
20 what?
4.
0.6. And then the second equation?
3 plus 15 equals 98.4.
Hey, that's the right answer. Okay, so V1 is 3.8. And V2 is 5.8. And what did the question actually ask for? IX. So IX, we would just need to plug in for V1. So 1.23 minus 0.1 V1. It's 1.23 minus 0.38 0.85 amps. Okay, any questions on that one?
For your I2 equation, why didn't you do 2IX is equal to all that?
Only because that's how it's given in the circuit diagram. Oh,
I
wait.
mean, why didn't you?
Oh, was that your question?
Yeah, why didn't you?
Why didn't I do what? Right here?
Why isn't it 2IX equals
Okay,
all that?
because IX is defined up here. So IX is defined as the current going through this, and so that's why. Does that answer your question?
Yeah, that makes sense.
Okay. Other questions? All right.
Can you go over the like what you entered in the TI-36 Pro?
Sure. You mean like?
Yeah, how you set up the table? Because I have the same calculator, but
sure.
I didn't know I could do that.
Oh, yeah, I'll show you. Hold on. Okay, so what you do is you do second, and I think it's the tangent button is system solve. And you can do a 2x2 or a 3x3. I think the 3x3 is easier because it just looks like the matrices that you enter. The 2x2 is supposed to be more friendly, and so with the 2x2, you're just putting in the coefficients, but you also have to put in the sign that goes in the problem. And so this one, I don't remember what the numbers were, so it was X was V1 and Y was V2, and so I just put in the value, the coefficients from the equations that we had set up, which were there 8 minus 1. So it's 8 and then a subtract, and then a 1, and then a 24.6, and then a 3 and a 15 and a 98.4. So you just put those in. So 8, enter, minus 1, enter, whatever it was, 24.8, whatever that was, enter, and then the next coefficient, enter, and then the sign, plus, and then the next one, enter, and then whatever's on that side, enter. And you just press solve. And then on this particular calculator, it'll give you the exact answer. If you want the decimal answer, it's the little button right above that. It'll turn it back and forth between fraction and decimal. Did that all make sense?
Yeah, thank you.
Mm-hmm. Other questions? Where you will really like this calculator is for doing complex numbers in circuits too. You don't know now how much you will like it, but you will. All right, so the problem on overdamped, underdamped, and critically damped, you should be able to recognize these kinds of responses. And so here I have two graphs, one showing a capacitor charging and one showing a capacitor discharging. And of the responses, one of them is overdamped, one's underdamped, and one's critically damped. And critically damped means that it reaches steady state the fastest. And the alpha and the omega naught is if you are using formulas to help you solve the circuit for serial or parallel. You compare alpha to omega naught to tell you whether or not it is overdamped or underdamped or critically damped. And so those are things that you'll compute from the values for your circuit. But so on this first one, does anyone know what the red curve is? Yeah, that one's underdamped. So anyone that looks like any curve that is oscillating and going up, above and below the steady state is going to be underdamped. And then the one that reaches the steady state fastest, and so it doesn't mean it gets there fastest. I mean, the underdamped gets there fastest, but it's not stabilized yet. The blue dotted line has that nice smooth curve. That one is critically damped. And then the one that's kind of falling short of everything, that one is overdamped. And the critically damped, you have alpha equals the resonance frequency. That's what omega naught is. And for underdamped, alpha is less than omega naught. And for overdamped, alpha is greater than omega naught. And the bottom one is the same, just kind of upside down, but you still would have the red dotted one, which is number 7, this is actually 1, 3, and 5. And number 7 is underdamped. Anytime you see that oscillation, that's underdamped. And that would have alpha is less than omega naught. And the blue one is critically damped. And that's alpha equals omega naught. And the green one is overdamped. And that is alpha greater than omega naught.
So if you just look at the overhead, just gonna be like it's gonna have less of a
Curvy.
right, less
Yep.
of a curve and stuff.
If you are just given the graph and you aren't given all three, if you're just given critically damped and overdamped, you can't really tell. Okay, you have to have something to compare it to. You can tell underdamped, but you can overdamped is going to be the one that is and notice that it's like compared to the the steady state voltage, it doesn't reach the steady state as quickly as the critically damped does. Other questions? All right. Okay, so now we're going to try one, and this is where I gave you all of this. Did y'all make your own formula sheet, or does she give it to you? Okay, so And including this, you have to put this on there?
If you want.
Okay, so, so this has everything that you need on it to solve a series or parallel RLC circuit using the time domain. And so what you'll do is you'll identify first whether or not you have a series or a parallel. And once you identify that, then you calculate alpha based on this bottom part here. For a series RLC, it's R over 2L, and for parallel, it's 1 over 2 RC. And then you compute omega naught. Omega naught is always 1 over the square root of LC. That's just a good thing to remember. The resonant frequency, that's a thing. And then you'll compare alpha and omega naught. And once you compare alpha and omega naught, you'll know what category you're in. Are you overdamped, critically damped, or underdamped? And once you know which of these you're in, you'll have some more things to calculate. If you have a series RLC, you will need to have IC of 0, and VC of 0, and VC of infinity. And if you're in a parallel RLC, you need VL of 0, IL of 0, and IL of infinity. And you'll need those no matter which category you're in. But then you have these coefficients to compute, just calculations to do. For the underdamped, you also need to have this omega D down here that's at the bottom. And for overdamped, you need to have S1 and S2, which are also down here at the bottom. So those formulas, and it's a lot of plugging in, but it's really not hard because it's kind of just plugging in once you identify what everything is. So let's see how to do it. All right, so first we have to figure out what kind of circuit we have. We assume that the switch has been here for a long time, and then at time t equals 0 it opens. So at t equals 0 it opens, and when that happens, this is the circuit we're left with. So that is a series circuit, so we know we have series. And L is 0.1 henries, and R2, that's the one that's in our transient circuit here, so that's the one we have to use, is 1.2 ohms. And the capacitor is 0.1 farads. So the first thing we do is we compute alpha and omega naught, which I did. So it's series, and so for series, I see that alpha is R over 2L. And R is 1.2, and 2L is 0.2, and so that gets me alpha equals 6. And omega naught is always 1 over the square root of LC. So that's 1 over the square root of L is 0.1, and C is 0.1. So that's 1 over the square root of 0.01, which is 1 over 0.1, which is 10. So that gives us that alpha is less than omega naught, and that tells us that we are underdamped. So for the underdamped situation, we need to have this omega D, And omega d is omega naught squared minus alpha squared, so I'll go ahead and compute that. So omega naught is 10 and alpha is 6. So that's square root of 100 minus 36, which is 64. And the square root of 64 is 8. So if you get here and you subtract and you get a negative number, then you weren't in an underdamped situation. Because if you get a negative number, that means that your alpha was bigger than your omega, and so that would be overdamped. Okay, now we need to calculate, we need VC of 0, VC of infinity, and IC of 0. So let's go and get those. So we need VC of 0, VC at infinity, and IC of 0. So when I look at VC of 0, I know this is important, that voltage on a capacitor cannot change instantaneously. So anytime you want to find VC of 0, you need to look at what was the situation right before the switch, because whatever it was right before the switch, it has to be that right after the switch as well. So right before the switch, I'm going to redraw this circuit. And it had been in that position for a long time, and that means that the inductor would act like a short circuit and the capacitor would act like an open circuit. So our inductor is going to act like a straight wire and our capacitor will act as an open circuit. This is 1.2 ohms and R1 is 0.4 ohms. And our voltage is 12 volts. To find the voltage on the capacitor, I see that the capacitor is open. And so you might say, well, the current through the capacitor is 0. And that is correct. IC of 0 is 0 because no current can flow through it. It's an open circuit. But that doesn't mean the voltage is 0. The voltage will be equal to whatever it's in parallel with. The voltage, just because there's no current, does not mean there's no voltage. And it's in parallel with the 1.2 ohm resistor. So VC of 0 is the same as the voltage across 1.2 ohm resistor because it's in parallel. And so to find the voltage across the 1.2 ohm resistor, I realize that at this point, even though I have all this stuff here over on the other side that I'm paying attention to, as far as the current is concerned, it's just going through this little circuit right here, and so I can do voltage division. So the voltage, so VC of 0, which equals the voltage across this 1.2 resistor, will equal my total voltage times the resistance there, which is 1.2, over the sum of the two resistances, which is 1.6. So that's 12 times 3/4. Our VC of 0 is 9. So I have IC of 0 is 0, VC of 0 is 9. Now I need, the other thing I need was IC at infinity. So at infinity, I'm on this circuit, which has no sources. So the energy is going to get dissipated through the resistor. So at infinity, there's no more energy in there. So VC of infinity will be 0. And we like that. The more zeros we have, the easier it is to do our calculations. So then if you go back and look at that formula page, you will see we have that there's a constant D1 that equals VC of 0 minus VC at infinity. And so D1 equals 9 minus 0, or D1 equals 9. And we have another constant D2, which is 1 over C IC of 0 plus alpha VC of 0 minus VC at infinity all over omega D. So C is 0.1, but that doesn't matter because IC of 0 is 0. Alpha was 6, VC of 0 was 9, minus VC at infinity is 0, over omega D was 8. That's 54 over 8, which is 6.75. So D2 is 6.75, and then VC of t equals e to the minus alpha t, so this is just the formula on that page, e to the minus alpha t d1 cosine omega dt plus d2 sine omega dt plus VC at infinity. So that's e to the minus 6t times d1 is 9. Cosine omega d was 8t plus d2 is 6.75. Sine omega d is 8t plus VC at infinity was 0. So here is my answer. Any questions on that? Nope. No questions? All right, moving along. Find CEQ at terminals A and B. So I thought this was nice that she said you'll have one problem that'll be either capacitor or inductor simplification, and those are not bad. So the only thing here is that it says at terminals A and B. Well, what does that mean? That just means we start at the other side and work this way. So we'll just work this way until we get it all down to 1 there. So let's see. Since we're looking at it from that point of view, we can see that these two, this is, okay, two are not affecting the capacitance of everything else because they're open. So, it sounded like someone was knocking. I guess that's someone in the lab over there. So, these two are not. I'm going to pause for a second while we see if there's someone trying to get in. I can keep recording. You just wait, hang out, talk. How many exams do y'all have? 4? Don't know?
I think somebody's moving stuff.
Oh, okay. All right, so these two capacitors are not going to be part of the capacitance as seen by A and B, because they're open on one end and they're not connected. So we're going to ignore those. So we can just look at these. And we see that these three are in series. Well, remember that you can't use product over sum for 3 things. You can only use product over sum for 2 things. So you have 2 options here. You can either do 2 at a time. So I could do like my 3 and my 3, and I know my 3 and my 3 would turn into a half. And then I could do product over sum with them, turn into 3 halves. I could do product over sum with 3 halves and 6. Or I can just use the long formula that says that if I have 3 things, that will be 1 over 3 plus 1 over 6 plus 1 over 3. So however many you have, it's 1 over each one added together. So I will do that because I don't have to actually do it. I can make my calculator do it. And we remember that capacitors add the opposite way from resistors. If they're in series, you have to do this funky kind of addition. And if they are in parallel, you can just add them. So this is 6/5. And this one was 6, and this is 5. So now I can add the 6/5 and the 6. And that would be 36/5. And then these are in series. That would be product over sum. 5 times 36/5 over 5 plus 36/5 is 36 over 66/5, which is 36 times 5 over 66. Thirty over 11, which is 2.95 farads.
So why can't you include the capacitors on the ramp?
Because they're not connected on the other end. They're not really. Let me. I think it would be easier for me to show you some examples.
The current doesn't go, right?
Well, there's no current here, so it's not. We're not really talking about the current. But if there were current, no current would go through it. it's, take me too long to open, but let me, like, remind you how capacitors work. So, if I have a capacitor, the way it works is I have charge plus charge on one side and minus charge on the other. That's why if I have capacitors in series, that each one will have the same charge, because we have the charge separation here. Whatever charge plus charge went on this one, the minus charge went on this one. So if I had something like this, I can have a plus charge build up here and a minus charge build up here, and a plus charge build up here and a minus here, but I can't have the same thing over here, because that's leaving this whole side negative without any, like, anything driving it. That's not a good answer. The negatives have to come from somewhere, and there's no reason why they would do that.
So if we were looking at terminal CD, we could ignore that 5.
Yeah, I think so. Let me look at it. Yes, if we were looking at terminal CD, we would ignore the 5. Yes. Yeah. Other questions?
Why isn't that 36 over 61 over 5?
I was gonna say that too.
Did I just make a math mistake?
25 plus 36.
25 plus 30. Oh, yeah, look at that, huh? What is it supposed to be?
61.
61 over 5. Yeah, because I copied this answer.
Yeah.
Yeah, so 61 over 5. So, yeah, sorry. I cannot, it's amazing that I haven't made more mistakes, but yes. Other questions? All right. So now we'll do an inductor, and now we're looking at L equivalent, and inductors add like resistors. And so here you can see everything is all connected over here. We don't have anything open like we had with the capacitors. And so these are in series and these are in series. So I can redraw this. Oh, that's a lovely inductor. So these three together become 6. These three together become 6. And they are in parallel with 3. They are in parallel with a 3 Henry inductor. So then the 6 in parallel with the 3, that would be product over sum, so that's 18 over 9, which is 2. So then I can redraw it. So these two in parallel are 2 Henries. And these two in parallel are also 2 henries. And that's in parallel with a 4 Henry inductor. And so that's 4 henries in parallel with 4 henries. And whenever you have two things that are identical in parallel, then product over sum will give you half the value. So this was a 4 in parallel with a 4 gives me a 2. And then I have a 4 here and a 3 here. And a 1 here and a 1 here. And my 4 and 2 are in series. And they make a 6. That's in parallel with the 3. And we just found that a 6 in parallel with 3 is 2. So 2, 1, and 1. And so I get 4 henries, if I did not make any mistakes. Except they were millihenries all along. I don't know how I was supposed to know that. Must have been somewhere else in the problem. Okay, any questions on that? All right. So now the moment you've all been waiting for. We're going to do a Laplace transform problem. And so this problem says to find V naught of t using Laplace transforms. And we would have to on this one because our voltage source, notice our voltage source is not constant here. And so we couldn't use just the formulas that we had on the other page. It says to find V naught of t. I realized after I wrote that it's not that hard to find V naught of t using Laplace transform, so I'm instead going to find I was going to say IC of t, but it doesn't matter. Whatever I find, there's only one I, so it could be the current through any of them. It would be the same. So the first thing I do is I redraw it in the S domain. So everything looks pretty much the same. The nice thing about the S domain, though, is that when you work with them, you can treat them all like resistors. They become impedances and not resistances anymore, and you can just add them the way you do with resistors. But we have to take the Laplace transform of everything. And so we have to take the Laplace transform of e to the minus t. Now, you've probably done this enough times that you know the Laplace transform of e to the at, but you have to write your Laplace transforms as well, or you're going to be given a table of those. So, the Laplace transform of e to the minus at is 1 over s plus a. I don't know which differential equations class y'all took, but I know that there's one of them around here that the differential equations class is like Laplace transforms and more Laplace transforms, and like all the Laplace transforms you could possibly want. And that's unusual in a differential equations class, but if you're an electrical engineering student, when you get to electrical engineering, you're like, oh, that's why we did all those Laplace transforms, because you will be seeing these again. This is not the last time you'll see them. So the Laplace transform of e to the minus t is 1 over s plus 1, because this is e to the minus 1t, and the Laplace transform of that is 1 over 1 minus 1, or s minus minus 1. The Laplace transform of a number, thankfully, is just a number. For an inductor, the Laplace transform is Ls. For a capacitor, the Laplace transform is 1 over Cs. So Ls here would be, L is 1, so this is just going to be S. And Cs, C is 1/10. So this is 1 over 10s, or 1 over 1/10 s. 1 over 1/10 s is the same as 10 over s. So nicely redrawn in the S domain, it would look like this. Okay, so now I can use what I know already about currents, namely I can use Ohm's law. I know V equals IR, except here it's not really R, it's the impedances. But I can just add all these together. Hold on, I have to answer this. Okay, so our voltage is 1 over S plus 1 equals, and our current is I, and our, it's actually, well, you call it capital I because I'm in the S domain. It's not in the time domain. The sum of our impedances will be 7 plus S plus 10 over S. Once you get an equation, your job is to isolate the thing that you're going to solve for and then take the inverse Laplace transform. And so usually that's going to be dividing both sides by something. And so I get I equals 1 over S plus 1 times 7 plus S plus 10 over S. Well, this is not yet in a form that I can take the inverse Laplace transform of. I want to clean this up a little bit. I need to get this S out of the denominator. I'm going to multiply this by S over S. And I get S over S plus 1 times 7S plus S squared plus 10. Now that's looking a little nicer. Just going to not really do anything here, just change the order. And it becomes 7 S squared plus 7S plus 10. Now, if this were an unfactorable quadratic, you have different options of what you can do with it. The way they usually teach it in the math department is to complete the square. The way that the textbook does it is you actually go ahead and factor it with using complex numbers. And either way is fine, but you're not going to have one of those on your exam. I'd be surprised if you did. So this one does factor. Into S plus 2 and S plus 5. So now I have an expression for the current, except it is not in the time domain. So in order to get it into the time domain, I have to take the inverse Laplace transform. And to take the inverse Laplace transform, I need to have things that look like things that I know how to take the inverse Laplace transform of. So when I look at my sheet, my table of inverse Laplace transforms, I need to get it into things that look like something kind of like this. And right now, in its factored form, it's not like that. I need to use partial fraction decomposition, which is always fun to say. So I know that this equals A over S plus 1 plus B over S plus 2 plus C over S plus 5. Now, I don't know if y'all know the shortcut way of figuring out I think it's a shortcut way, figuring out A, B, and C. So to figure out A, I take my expression here except for the S plus 1. I was trying to be careful not to make my 5s look like S's. Whoever decided S was the right variable to use for this, horrible. Because my S's and my 5s are absolutely identical. Okay, so I leave out the S plus 1, but I evaluate this at -1, at the value that would make S plus 1 equal to 0. So A equals -1 over 1 times 4, so 1/4. And B equals, I leave out the S plus 2, and I evaluate this at S equals -2. And I get -2, S plus 1, -2 over -1 times 3, which is 2/3. And C equals S over S plus 1, S plus 2, evaluated at -5. And I get 5/12. So that means I equals -1/4 over S plus 1 plus 2/3 over S plus 2 plus 5/12 over S plus 5. And now I take the inverse Laplace transform of this, and I get I of t equals -1/4, and the inverse Laplace transform of S plus 1 is e to the minus t plus 2/3 e to the minus 2t plus 5/12 e to the minus 5t. And this is all times the unit step function. Now, let me just show you, since the problem said to find V0 of t using Laplace transforms, how we would do that. Okay, so if I wanted to find V naught was at the capacitor, so this was right there. If I wanted to find that, now that I have this in terms of impedances, I can use voltage division. So I could say that V naught equaled my total voltage times my impedance that over the part that I'm looking for over the sum of the impedances. So if I bring that S down to the bottom, I already have this S that I can multiply through here to get rid of my fractions there. And you can see that we end up with a very similar fraction to what we had before. It would just break down and have different coefficients if we were to do the partial fraction decomposition. So to finish this, which I'm not going to do, you would do partial fraction decomposition and then take the inverse Laplace transform. All right, so that was all I had prepared. Like I said, I'm going to look and see if I can find some videos. Do y'all have any other topics that you are interested in seeing stuff about, or any other questions before we call it a day?
When you return in the estimate, you can do the voltage sources because they're zero, so they're one.
Because the state before the zero is, there's no.
Oh, I see what you're saying. Yeah. Okay. Excellent question, because I always forget to do that. So I didn't do it because I forgot to look, but I got lucky, I hope. I did get lucky? Okay, yes. Okay, so the question was, why did I not include the voltage sources here? And the answer is because those voltage sources come from if you have current or voltage prior to time t equals 0. And I didn't because our voltage source was a unit voltage, had u of t on it. So that meant before time t equals 0, it was 0. So if you go back and look at it, the voltage source was e to the minus t u of t, which meant at t less than 0, it equals 0. And so before time t equals 0, there was nothing going on, and no voltage. This is 0. And so no current through the inductor and no voltage across the capacitor. But yeah, you do have to look at that, and I always forget. And so I just got lucky. I picked this example this morning because I wanted to pick a straightforward example, because she only gives straightforward ones. I've never seen her give one that's really messy. And I just kind of lucked out. Yeah. Okay, other questions? And nothing in particular that y'all want me to look for in terms of videos? Alrighty then. Well, I'm going to sign off, and I will. Would anyone like a copy of like if I export my notes to a PDF? Would anybody like a copy of that? If you do, send me an email, And I'll try to figure out, I'll probably send a link out to the recording to the the Digital Logic 2 class, and then anybody who's not in that class, if they know someone who's in the class, maybe you could ask them. All right, bye.